Hello, my name is Soo-Kyung Kim. I'm going to give the presentation on our paper named Robust Policy Learning via Offline Skill Diffusion, which is accepted in the AAAI in 2024. Currently, I'm the PhD student in the Department of Computer System and Engineering, and my lab is Computer System Intelligence Lab, and my advisor is Woo Hong-wook professor. Um, our lab's research topics includes mainly the reinforcement learning and imitation learning through use and the robotic controls. And currently, we also do the embodied AI and multimodal learning, and we also do the large language model. We also do some research about the intelligent systems, including network systems and storage systems. If you want to find more information about our lab, then you can go to this URL. There's going to be the projects that we're doing currently and the students and the research topics and the recent publications also. So we have some recent publication in the CVPR, which is about the time constraint in the embodied control. We also have several papers accepted for the AAAI. The first one is about the skill-based learning using the diffusion models, and the second one is about the semantic skill transfer in the cross-domain settings. And the last one is about the risk condition RL. And we have several more publications in the top tier AI conferences. So if you have any questions or if you want to join our lab, then feel free to contact us through this email here. So before we start, I'm gonna first explain about the little bit about the skill-based reinforcement learning. So we have the bunch of training data sets, which is collected from diverse set of tasks. And this training data sets is consist of a trajectories, which is represented as a sequence of states and action pairs. Then the object of skill-based RL is to accelerate the adaptation to long horizon tasks by leveraging pre-trained skills learned from given training datasets. And the skill here is defined as a sequence of H consecutive actions. So we have the bunch of training datasets collected from the multiple tasks. We first extract the skills, the sequence of actions from the offline, these training data sets, and using the learned skills, we're gonna wanna to quickly adapt to the new tasks in a different domain. The conventional skill-based reinforcement learning approaches adopted the deep latent variable model to learn as a skill representation or the skill embeddings. These approaches mainly employs the skill encoder, skill decoder, and a skill prior. So the skill encoder maps this action sequence to a skill embedding. Then the skill decoder reconstructs the actions from the skill embedding, sample from the skill encoder. So through this encoder-decoder architecture, it can learn a skill embedding, which is kind of a abstractions of a action sequences. Then the skill prior maps the current states to the skill embeddings. However, these conventional skill-based learning approaches often operate under the premise that the target domain for a downstream task was presented in the offline datasets. Thus, these approaches struggles in choosing suitable skills for a downstream task that is in the different domain. So our work addressed the problem when the domain of offline datasets, which we're going to refer to source domains, are different from the domain of the downstream tasks. For this, we propose offline skill diffusion, the dual skill framework, which expands the skill diversity that goes beyond the datasets, thereby enables the execution of compatible skills for the downstream tasks that belongs to the different domains. Our dual skill framework consists of two main phases. The first one is the offline skill diffusion phase, and the second one is downstream learning phase. First, in offline skill diffusion phase, we employ guided diffusion-based decoder in conjunction with a hierarchical domain encoder to disentangle skills into the domain invariant and domain variant embeddings. The hierarchical domain encoder consists of a domain invariant encoder and domain variance encoder. These encoders play distinct roles in which domain invariant encoder is responsible for encapsulating features necessary to reconstruct fundamental action sequences pertinent to achieving goals, while the domain variant encoder is tailored to capture the features related to domain variations. For the decoder, we utilize the guided diffusion model with two components where one is conditioned on the domain invariant embedding, while the other focuses on the domain variant embedding. By employing the hierarchical domain encoder and guided diffusion-based decoder, our dual skill framework is capable of generating diverse action sequences that encompass different combinations of the domain invariant and domain variant features. Second, in the downstream policy learning phase, we exploit the disentangle embeddings via a high-level policy. The embeddings are then fed into the frozen guided based decoder to generate appropriate executable skills. Now, I'm going to explain each component in our dual skill framework. For hierarchical domain encoder, we employ domain invariant encoder and domain variant encoder. The domain invariant encoder maps state action sequences into a domain invariant embeddings, and domain variant encoder maps domain invariant and domain parameterization into domain variant embedding. These encoders are trained with the evidence lower bound loss using with the skill decoder. We also employ a domain invariant prior and domain variant prior, which are used to initialize the high-level policy in the downstream policy learning phase. The domain invariant prior maps current states to domain invariant embedding. And the domain variant prior maps domain invariant embedding to domain variant embedding. These priors are jointly trained with encoders by minimizing KL divergence loss between each respective encoder. For skill decoder, we adopt the diffusion model. So before I explain about our diffusion-based skill decoder, I'm gonna first explain about what the diffusion model is. The diffusion model, which is also known as denoising diffusion probabilistic model, is a generated model which is widely used in vision studies recently. So, unlike other generated models, it is consists of forward process and the reverse process. In the forward process, we iteratively add small amounts of Gaussian noise to the datasets. So after we add the Gaussian noise to the datasets iteratively, we obtain some random noise. In the reverse process, we gonna obtain the true sample from the Gaussian noise input. So the DDPM learns a model to approximate this conditional probabilistic model, which converts the noised input to the denoised version of the predecessor to run the reverse process. So as you can see the above image, from the Gaussian noise on the right side, some random noise on the right side, if you have learned the diffusion model, you can reverse the process to obtain the true sample on the left side. So this diffusion model is also used in the DALI 2, and currently this model is widely used on the imitation learning too, because it is known to be good at generating the samples and model the multimodal distributions. So for our skill decoder, we adopt this diffusion model. Our decoder reconstructs an action from a random noisy input by sequentially predicting the marginally denoised version of its predecessor. To further align with the hierarchical domain encoder, which consists of the domain invariant encoder and the domain variant encoder, we slightly modify the classifier-free guidance to divide the decoder into two separate parts. So we also separate our skill decoder into the domain invariant decoder, which reconstructs the actions that consistently execute the designated task across the domain features. And we also employ a domain variant decoder, which generates the guidance that encapsulates the domain variant features. So our skill decoder is defined as the combination of the both domain invariant decoder and the domain variant decoder. And for downstream policy learning phase, we employ a high-level policy. This high-level policy is initialized with our domain invariant prior and the domain variant prior. So this high-level policy generates both the domain invariant and domain variant embeddings. And these entangled embeddings are then fed into the frozen guided diffusion-based skill decoder. By combining arbitrary combination of domain invariants and the domain variant embeddings, our dual skill framework is able to generate suitable skills for downstream tasks in the different domains. For downstream task adaptation, we explore two different scenarios: diffusion imitation and online reinforcement learning adaptation. For evaluation, we use the multi-stage meta world, which is implemented based on the meta world simulator benchmark. In this meta world environment, the multi-stage task is composed of a sequence of existing meta world tasks called the subtasks, such as slide pug, push button, closed drawer, or the open door. And to emulate the different domain in the environment, we deliberately add variations to either reward functions or the transition dynamics. Specifically, we modify the reward function by setting the time constraints to configure the speed domains, and we incorporate energy usage consideration to configure the energy domains. Furthermore, we vary kinematic parameters for transition dynamics to configure the wind domains. For baselines, we implement several imitation learning and skill-based RL algorithms, including behavior cloning approaches, the BC, and SPI-RL and FIST. The baselines with asterisk signifies both the high-level policy and the decoder is fine-tuned. And we also categorize domain into 4 different levels based on the domain disparities between the offline datasets and the downstream tasks. As you can see in the above table, our dual skill framework consistently maintains robust performance across all domain and the levels, achieving a small degradation of 7.6% at average, and our dual skill framework outperforms the most competitive baseline, FIST, which achieves an average degradation of 25.3%. So we also conduct experiments in online RL settings. We compare dual skill framework with BC plus SAC and the SPI-RL algorithm. So as you can see in this table, dual skill framework exhibits superior performance compared to other baselines for tasks in different domains, especially outperforming the SPI-RL by 89.16%. And we also conduct the evaluation studies on the skill diffusion to show the effect of our hierarchical embedding structure and the guided diffusion-based decoder. Here, the DU is the variant of SPI-RL, which utilizes the diffusion model for the skill diffusion, and uses the knife embedding structure. And the HDU employs hierarchical embedding structure and uses naive diffusion model for the skill decoder. As you can see in the evaluation studies for the skill diffusion, our dual skill framework, which uses the both hierarchical embedding structure and the guided diffusion-based decoder, it shows the benefits. It shows the improved performance compared to the other variants, showing the benefits of our proposed architecture. The left figure, we also visualize the domain invariants and domain variant embeddings generated by our dual skill framework separately in two distinct speed domains, the fast domain and the slow domain. The labels T1 to T4 correspond to subtasks numbered from 1 to 4. We observe that domain invariant embeddings are paired together, reflecting their invariant knowledge across the different domains. While the domain variant embeddings are grouped with respective to the domains, this implies the variability between the domains. The right figure shows the performance with respect to the samples or the time steps for downstream policy learning in few-shot imitation and online reinforcement learning scenarios. As you can see, the dual skill framework exhibits robust performance with only a 4.89% drop from 1 to 20 trajectories, whereas the most competitive baseline FIST shows a notable performance drop of 13.96%. Furthermore, dual skill framework efficiently adapts to the downstream tasks in online setting, enhancing the performance with only 50K samples. In conclusion, we presented the dual skill framework, a novel approach designed to bridge the gap between the given datasets and the downstream tasks that exist within different domains. So we devised the offline skill diffusion framework, which employs the guided diffusion-based decoder in conjunction with the hierarchical encoders to effectively disentangle domain invariant and domain variant features from skills. Our framework enables the generation of diverse skills capable of addressing tasks in different domains. Our framework stands apart from existing skill-based learning approaches, which are typically limited to adapting within the domains encountered during skill pre-training.